Welcome back to today's episode on Chemistry Made Easy with Bright Edo. In today's video lesson, I'll be teaching on a very important aspect on radioactivity, basically nuclear chemistry, and it is on binding energy calculations. Now, the first question you ask yourself, what is binding energy? This is the energy required to break the nucleus of an atom to produce its components. And what are the components of the nucleus of an atom? They are just two components. We have the protons and the neutron. So the binding energy is the energy required to break this nucleus to yield its components, which are protons and neutron particles. So binding energy for calculation purpose is given with E. So the energy or binding energy has a formula and it is changed in mc squared. So the question you ask yourself, what is E here? E is the binding energy. And delta M is the mass defect, or you say the change in mass defect. And C is speed of light. Speed of light has a constant, and what is the constant for speed of light? It is 3 times 10 raised to the power of 8 meters per second. So this is the value for the speed of light. So you can see here for binding energy is equal to the mass defect times speed of light. We now square the value for speed of light and we'll get our answer. So in the course of today's lesson, we'll be learning how to calculate mass defect. After calculating mass defect, we now move over to calculate the binding energy. Because without the mass defect, we can't get the binding energy for that element. So let's see a question and let's apply this formula to it. Now let's quickly solve this question so as to master how to solve problems under the binding energy. Recall earlier I gave the formula for binding energy to be delta mc squared, whereby delta m is the mass defect and c is speed of light and E is the binding energy. Now let's read this question. Now, given that the actual mass of helium is 4.0026 AMU, calculate the following. A, calculate the mass defect. B, calculate the binding energy. And C, calculate the binding energy per nucleon. Now, we are coming there. But first thing first, we must learn how to calculate is the mass defect. How is mass defect calculated? Now, for A, mass defect. Now, it is very easy. To calculate mass defect, we simply say delta M. Now, mass defect has a formula, and it is calculated mass. It is calculated mass minus actual mass. It is calculated mass minus actual mass. Now, if you check the question carefully, you can see they gave us the actual mass for the helium atom. So what we have to do now is to calculate the calculated mass or solve for the calculated mass. So how do we do that? Very easy. Now, let's bring out this particle out. Let's bring it here. So helium 4-2. Now, first thing first, what is the proton number of this helium particle? It is 2. The proton number of the helium particle is 2 because the number down here, the atomic number and the proton number, they are the same thing. So the proton number for this particle is 2, or for this atom is 2. Now, secondly, let's calculate the neutron number. So let's say proton number is equal to 2. So how do we calculate neutron number? Neutron number is calculated by saying mass number, okay, minus atomic number. Now, what is the mass number? The mass number is 4, and what is the atomic number? 2. So what is the neutron number? 2. So the neutron number for this same helium atom is 2, whereby the proton number is 2. So this is something we must take note of first. So how do we now calculate for the calculated mass or solve for the calculated mass? Because the actual mass is already given. So we are looking for the calculated mass so as to solve for the mass defect without stress. So you quickly say here for protons and here for neutrons. Now, for the proton, you already know that the proton number here is 2. So you bring it here. Same with the neutron number to be 2. Now, what was the proton mass given the question? This is the proton mass. So we see 2 times the proton mass, which is 1.0078 AMU, times 2 times the neutron mass, which is 1.0087 AMU. So let's calculate for both masses, okay, for the proton mass and the neutron mass. So we want to get our calculated mass. So we say 2 times this value, which is 1.0078. So we simply get 2.0156 AMU. And let's do this. We get 2 times 1.0087, that is 2.0174 AMU. Okay, 0174 AMU. So the next step to be taken is to add both values. So we add both values. So when we add the both values, let's see what we get. We get the calculated mass to be 2.0156 plus 2.0174, so give us 4.033 AMU. So this is the calculated mass for for this helium particle. Now, summarily, it must be noted to solve for the calculated mass, because the calculated mass is the value that is not given in the question. So what you simply do is to first of all bring out the atom given in the question. Most times, sometimes it can be this, sometimes it can be other elements. So dependent on how it comes. So in this case, it is helium. So we simply calculate for the proton number of helium. What's the proton number of helium? 2. We simply calculate for the neutron number of helium. What's the neutron number of helium? 2. So after doing that, we simply come here, and that our value we got, we times the mass, and the mass is a constant. Okay, we times with this and times for the neutron mass, so we got this. So at the end, you now add both values. Now this value we just got is the value for the calculated mass. Okay, this is the calculated mass for the helium particle. So next step to be taken is to solve for the mass defect. And what is mass defect? It is basically calculated mass minus actual mass. So basically, mass defect becomes, that's delta M, becomes, what's the calculated mass? Is what we've got in 4.033 AMU minus. Now, it must be noted that the calculated mass is always bigger than the actual mass. You can see 4.033 is bigger than 4.0026. So it's always bigger. So we say minus the value, which is the actual mass, which is 4.0026. So what becomes the value for the mass defect? What becomes the value for the mass defect? So it's 4.033 minus 4.0026. So it becomes 0.0304 AMU. So this is the value for the mass defect. So we've actually solved for the first one, which is 0.0304 AMU. So this is how mass defect is being calculated. So let's quickly move over to the other, which is the binding energy. Now let's go ahead and solve for the binding energy in the question. Now, before we do that, let's bring our mass defect value we've gotten, which is 0.030 4 AMU. Now, we'll now go ahead to solve for the binding energy. Recall, binding energy is basically E is equal to change in the mass defect C squared. Now, normally, we are to bring this value here and impute and times with our speed of light and get binding energy, but we don't do that. We don't do that. What we simply do first of all is to convert the mass defect from AMU to kilograms. This is something that must be noted. When you are done calculating the mass defect, convert the mass defect from AMU. What is AMU? Atomic mass units, to kilograms. Take note. So we have to convert this value to kilograms. Now, how does it work? It must be noted that 1 kilograms is equal to 6.022 times 10 raised to the power of 26 AMU. This is something that must be noted. Now, x kilograms, which we are now looking for, will now be equal to what we got. So it's 0.0304 AMU. So cross multiply. So when we multiply, x kg becomes, that is 0.0304 dividing 6.022 times 10 to the power of 26. Okay, so our x kg becomes 5.0482 times 10 to the power of minus 29 kilograms. So this is the mass defect. Now, this is the value we are to impute in the formula, not this one we got initially. It must be noted, whenever you are done solving for the mass defect, by doing following those processes I gave. After that, you will now quickly convert that value from AMU to kilograms, because the binding energy here is in joules. So it must be noted that the speed of light basically is c, and it is 3 times 10 power 4 now 8 meters per second. So we simply say binding energy will now be equal to the value, now this one not this not this, so it is 5.0482 times 10 power minus 29 times the speed of light, and the speed of light is 3 times 10 power 4 now 8, all squared. So let's press this in our calculator and get for the binding energy for the helium atom. So it becomes 5.0482 times 10 power minus 29 times into bracket 2, 3 times 10 power 8, close the bracket, raised to the power of 2. So our binding energy becomes 4.5434 times 10 power minus 12 joules. So this is the binding energy for the helium particle or the helium atom. Now you can see at the end of this question they are asking us to calculate the binding energy per nucleon. How is binding energy per nucleon calculated? Now it must be noted that nucleon number, okay, is same as mass number. Nucleon number is same as mass number. So what does it mean? So if they are asking us to calculate the binding energy per nucleon, so basically they're asking us to like divide the binding energy with the nucleon number, because per means divide. So binding energy per nucleon. So let's say with an acronym, binding energy per nucleon is equal to the binding energy value over the nucleon number. Okay, this is something that must be noted. Binding energy per nucleon is solved by saying the binding energy we've gotten now over the nucleon number. Recall the nucleon number is same as saying the mass number. What's the mass number in this particle? It is 4. You know, mass number is always up and down is the atomic number. So we simply say for the binding energy per nucleon, it is the binding energy we've got, which is 4.5434 times 10 power 4 now 12. So okay, minus 12 um over the nucleon number, which is 4. So what becomes the binding energy per nucleon value? So we simply divide. So we simply say 4.5434 times 10 power minus 12 all over 4. So we get the binding energy per nucleon to be 1.14 times 10 power minus 12. Okay, this is the binding energy per nucleon value. So I believe now you now get how problems under this aspect are being tackled. You have to follow the process step by step. Recall to calculate for the mass difference, you simply calculate your proton number and neutron number in the atom. After doing that, you now times those values with the proton mass and the neutron mass. After that, you add it together to get what? The calculated mass. And recall, calculated mass is always higher than what? The actual mass. So at the end, you now subtract, to get your mass defect, you now subtract the calculated mass from the actual mass. So you now get the value for your mass defect. And the mass defect value first, when you solve, will be in AMU. You have to convert it to kilograms. After doing that, you will now bring down your value from in kilograms to the formula and get your binding energy. And after getting binding energy, if the question says calculate the binding energy per nucleon, you simply go to the atom back and check the nucleon number. Recall I said nucleon number is also called the mass number. Mass number is always located up. So you now divide the value you've gotten over the nucleon number. So what will happen now? I want to bring a question here so you solve and provide the answer in the comment section below. So if you like this video, do well to subscribe to this channel and share my videos with your friends. Now this is the question you'll be solving and you provide the answer in the comment section below. Now the question says the discrepancy in mass of the formation of a radioisotope is calculated to be this value. So what is actually this value? This value given is the mass defect. Now the question, they've already given us the mass defect, so we are not to calculate the mass defect again. They've already given us the mass defect already. They said the discrepancy in the mass, that means the mass defect of the formation of radioisotope is calculated to be this. So this is the mass defect. They've already calculated the mass defect for us. So what we have to do now is to convert the mass defect from AMU to kilograms. After that, we calculate for our binding energy. Okay, the binding energy of that whereby 241 here is the mass number of the atom. The atom is unknown, but it's the mass number of the atom. And also they say the question says calculate the binding energy per nucleon. So after solving the binding energy, we now divide by the mass number or the nucleon number. That's why it's per nucleon. So you can remember I said nucleon number is same as mass number. So basically, I believe now this aspect on the binding energy calculation is made easy. So if you like this video, do well to hit the subscribe button and share my videos with your friends. So thank you very much. God bless.